Adams State College. Great stories begin here.
Okay, so our next presentation are by two of my students, Traci Hill and Jessica Helweg. This is a project, an independent project that they worked on last semester in my plant physiology class. And so they came up with the idea, they come in with the experimental design. It was really very clever experimental design. They had to use their engineering skills. And they also spent several hours sectioning and got really good at some techniques that they may never need to use again. They're both biology majors, both juniors. Their emphasis is wildlife biology. Jessica wants to go on into animal rehabilitation. And Traci in wildlife illustrations. And she has one of her illustrations here. She's really quite talented. So take it away.
Thank you. I'm Traci, and this is our presentation. We did our experiment, actually three kind of intertwined, kind of more bang for your buck. And it was the effects of ethylene and wind on Clink cell development. And we used sunflowers in particular to test the mechanical and both chemical/hormonal influences.
The scientific name of the sunflowers is the Helianthus annuus. It's one of the few crops that originated in the United States. Commercial uses include like premium oil. The sunflowers account for about 14% of the world's seed oil. Industrial application includes like certain paints, varnishes, and plastics. In Europe, they're used to make soap and detergent. Also in Europe and Russia, they produce about 60% of the world's sunflower. The sunflower, we chose the sunflower because it's grown pretty quick, within a couple weeks. It has extended primary growth. It is also a good source to show increased Clink cell growth during the experiment because the Clink cells are located near the epidermis or the skin, which is adjacent to the vascular tissue, which includes the xylem and phloem, which helps with the transport of water and sugars, starches, all the necessary minerals. Sunflowers go very erect, so the mechanical stimulus of the wind was pretty obvious. I mean, it caused them to bend very obviously once after a couple weeks. So,
since we used mainly, actually the experiment only lasted about 3.5 weeks, and during that time we had just little seedlings to work with. So the areas of interest are this two up here. And as far as the cell differentiation went past the shoot apical meristem, we had just the initial starts of Clink cells around the epidermis, around the epidermis and the vascular tissue.
We tested the effects.
Oh, sorry. Are you going to do that? Okay.
Yeah, it's yours. Sorry.
The Clink cells that actually the word cola for Clink comes from the Greek word meaning glue, and it actually has a milky white sheen to it, resembling glue, and it actually holds the plant together as a biological adhesive. It provides structural support, and when turgid, it can swell to up to 150%. It's also, when it's also turgid, it can also provide a flexible rigidity, and especially these guys growing, beyond 8 feet, that rigidity in places like Kansas where it's super windy, it needs to be in place. The Clinkema are elongated cells, and they have unevenly thick walls, and as you can see here, maybe up around this edge, they have, you can see dark blotches, and those are actually the unevenly thickened walls. Those help differentiate the 3 different classes of the Clink cells. Sorry. In the sunflowers, they're eudicots, so the vascular tissue is not just around the epidermis here, but it's also around the vascular tissue. As you can see this little swirly area here, there's also Clink cells there.
For part of our experiment, we used ethylene and the effect of it. It's a gas and it's a senescence hormone. It helps stimulate shoot and growth differentiation. It also helps with adventitious root formation. Like abscisic acid, it's the only member of its class, and of all the known growth substances, it has the simplest structure. We had to use ethylene glycol though because we couldn't find any pure forms of ethylene, and also we couldn't find a specific way to administer it because of the gas, and money with the department couldn't allow for a good chamber to release the gas and hold it within. Ethylene glycol though is a very viscous solution. It has a boiling point of 102 degrees Celsius, and it is also used as antifreeze in a lot of different things.
Our experiments, like we said, we did 3. They kind of intertwined. And the first was to test the effects of wind on the Clink cells, on both the growth and the development. And the wind was a practical and easy form of mechanical stress that we could administer. And because it's made of the cellulose matrix is what the Clink cells are made up of, it actually would have a direct response to the wind stimuli. The ethylene, as we said, is a senescence hormone, but it also helps in cell differentiation. And so we thought, well, you know, if we administered that and the wind at the same time, would those two interplay with each other?
So we made the hypothesis, you know, that seedlings exposed to wind will develop more Clink cells than growing in the windless conditions. The effects of ethylene upon seedling growth will include like a triple response of stunting, early shoot maturity, and eventually chlorosis, which could also lead to necrosis in the long-term run. Ethylene exposures of seedlings would cause the increase of the Clink cell development along with the wind.
Our methods, we planted 3 seeds in 20 pots, and we only needed 5 plants for each one of the treatments. We actually had 6 because it's always good to have a backup, and then of those 6 we chose the 5 hardiest. Our treatments were ethylene with wind, ethylene with no wind, no ethylene with wind, and no ethylene or wind. And the interplay of those are that the third one, no ethylene with wind, and the ethylene with no wind, those served as controls for the top 2. And then the ethylene with no wind and then the no wind, obviously, those served as the controls for both 1 and 3. And then, of course, number 4, the no ethylene or wind, served as a base control for the other 3 that did have either chemical or mechanical stimuli. The growing time overall was 3.5 weeks. That's from the time we planted the little seeds until their hypocotyl crested the soil. And then from that point, the 17 days after that is the time that we administered the treatments.
This was our setup here. It's kind of hard to see, but you know, we just fashioned cardboard boxes to make sort of tunnels and then put plastic wrap over it and taped it all around. And we just had our plants at the very end, and then we would put the little fan in the very front of the tunnel that we created and put the plastic around the back to keep the ethylene within the chamber. So
the super high-tech stuff was about 1 foot by 1 foot and about 2.5 feet long. And the fact that it was cardboard with plastic wrap over the top was actually really good because it prevented excessive transpiration and it allowed a flow-through system, so that way the plant wouldn't fix oxygen. There wouldn't be an accumulation of oxygen. It'd have constant fresh air flowing through.
And the staining process. Well, the first thing we did is you took cross sections from each plant, the top, middle, and bottom, and we used a razor to make transparent sections, and on each slide we put, well, before we put them on each slide, we first had to put them in water for 30 seconds, and then put them in the dye for about 60 seconds, and then put them back in the water for 30 seconds to get rid of the excess dye. Once we did that, we put 2 plants on each slide that we made and labeled them middle, top, bottom, and we mounted them. We used nail polish, clear nail polish to mount them, and we had to, you know, press them down, hopefully not crushing them so we could still look at them, and then we just allow them to dry, and this took a very long time and it was very tedious, so.
Good exercise in patience.
Yes.
Let's see. There's our beautiful setup. These trays here, these right here, that's where we soaked and rinsed the stain, the toluene blue, from our slices. And then this is the stain, the toluene blue. And then we mounted them on the stains. Those are in the blue boxes. I'm getting better at aiming this. And then with the labeling and our fancy, yeah, that's it. Our fancy adhesive / nail polish. Okay, our results from these slides. We found that the ethylene with the wind had a thick noticeable band, and it had significantly more bundles than any other. The ethylene with no wind formed a ring also, however the bundles were fewer cells per bundle. The thinner bundles with the ethylene with wind, but not very much. And then our ethylene with no wind had the fewest number of cells, and they were sparsely positioned in a ring-ish. And that's
our beautiful slides. So we kind of tried our best to make a graph so everyone can see a visual of our results. We counted the number of cells in each width of the bundles and guesstimated, like within the width, the percent of colmencema cells that were seen in each cross section. With each treatment, you can see, like at the bottom, the ethylene wind, we got about 100% improval. Like it had the most, obviously, out of them all because that's what we had hypothesized. And then ethylene no wind had the most, ethylene wind had the third most with 67%, and then our control had the least.
And here is kind of a composition of the slides up close. The larger dark band here is the ethylene with wind. That's both the mechanical and the hormonal stimuli. And then over here, right here, that is just the wind alone. Whereas there's not much difference. I drew it a little skewed so I could tell the difference. But that's just the ethylene only. And then the ones with just 1 or 2 cells per bundle here, the darker purple cells, those are the control cells, the ethylene with no wind. And as our conclusions, as you saw from the slide, that you can manipulate the presence of the Clink cells, and either hormonally or mechanically, and then they are designated for structural support. These tissues are the primary source of flexibility for all plant species, and that have them, I should say, and they. Yeah, I said that.
In our discussion, I mean, in the end, our initial hypothesis was supported from what we found in our experiment. The degree to which we presented or what we found could have been enhanced quite a bit, but yeah, so.
As far as implications go with this, because you can manipulate the amount of Clink cells and make the plants more structurally sound, that could possibly have, either privately or commercially, it could have implications as far as, making the geographical distribution, making the plants more viable in a larger range. And let's see, the questions that arose, many of them, and we had, if the stimuli were put in place initially from day one, as far as the ethylene goes, would that have a different effect. And then, of course, you can only have the wind influence them from the time that the little hypocotyl crests the soil. If you remove that stimuli, would the Clink cell from that point forward return back to its normal stasis, or would it continue on with the manipulated formation? And to what degree can you manipulate those Clink cells?
Some improved suggestions that we found was we didn't start our treatment with the ethylene from day one, which we should have done. We started it a week later after the seedlings had begun to develop. If we had done that, we probably would have seen more Clink cell development and just better results. And the wind source we used wasn't very strong. We had like a little itty bitty fan to fit in that little tunnel. And it provided enough stimulus to see the effects, but if there had been more, there probably would have been a substantial amount of increase in Clink cell development. So also, we found that during the time we administer the treatments of the ethylene glycol, we added it to the soil right near the stem, and also we added it to the leaves. We found that it probably would have been better if we just had applied it to the soil. That way it would have gone directly to the roots and up through the stem to the rest of the leaves. And when we applied it to the leaves, they almost died initially and experienced senescence. So we couldn't really use that in our results because they were just dead. So.
We also, as she mentioned, with the wind tunnel, had we had a more extreme source of wind, that would have played into Krog's rule, which states that you go to an extreme environment if you want an extreme example phenotypically, or the way that the animal/plant responds to that environment. If you want kind of a middle of the ground type thing, sample to look at, then you do what we did and you put, a weaker wind force. But had we put a more extreme, source of wind in there, then we would have seen a lot more results. Any questions?
Adams State College. Great stories begin here.